Hi there, folks. Today we're looking at surface areas and volumes of spheres. And I don't have a sphere defined here. I think most students have a working understanding of what this is. Essentially, it's a ball. It's a kind of a three-dimensional depiction of a circle. And when you look at the exact definition of a sphere, it kind of is the three-dimensional version of a circle. It's defined as the set of points all equidistant from some center point. But we're talking equidistant in a three-dimensional space. And if I go equidistance in all directions in a three-dimensional space, what I end up with is a sphere. Okay. When I use that same definition in a two-dimensional space, I end up with a circle. Okay. And so this is really just a three-dimensional version of the circle. All right. The surface area for a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. And we're just going to use these formulas in order to find values of the sphere, okay? To find the surface area and to find the volume, okay? For example, if I look at this guy, it says find the surface area and volume of each. And so if I look at this first one, right away I can kind of see, we can think of spheres as having being made up of a bunch of congruent circles. And if you think about spinning that circle, if I just kind of look at one of those circles around the circumference of this thing, I can use that to kind of depict the radius and those kind of things. And so as I look at this particular sphere, it has a radius of 4 centimeters. And so to find the surface area, I just plug it into my formula, 4 pi r squared. And the radius this time is 4. And so if I plug away on this, let's see, 4 squared is 16, and then 16 times 4 is a 64. I could leave this in terms of pi. That's 4 pi, and that's square centimeters. And so there's my surface area. I could also plug that into the calculator. Let me do that real quickly. Using my pi button, I could also say the surface area is 201.06. And again, it depends on the context of the situation. I might want the exact surface area, or I might want the rounded off version. Now let's talk about the volume. The volume is 4/3 pi r cubed. And so once again, I just plug this into my formula. The radius this time is the 4. And then I can use my calculator to kind of simplify this thing. So 4 to the third power is 64 times the 4/3. Let's see, that's going to give me, if I leave this once again in terms of pi, that's going to be a 256/3, and that's pi cubic centimeters. Or if I plug this into the calculator, it gives me a volume of 268.08 cubic centimeters. And one of the slight extra challenges to this is because of that kind of strange fraction that's built in here, the 4/3. It's not very often that it's going to reduce nicely. So when I do the exact form, I'm probably going to have some kind of fraction in there, or it's just more likely to happen. Okay. If I look at this one, now I have the diameter of the sphere given. And so thinking about the radius of this thing, if the diameter is 10, the radius would be 5 meters for this one. And so once again, I just head over to my formulas. I say, okay, I want the surface area. The surface area of this thing is 4 pi r squared. The radius this time is a 5. And so if I simplify and kind of leave this thing, let me give myself a little more space. Just leave this thing in terms of pi. 5 squared is a 25 times the 4 is a 100. So 100 pi, and that's square meters. I could also plug this into the calculator, write it as a decimal. And that gives me 314.16 square meters. And again, it depends on the context. Sometimes I'm going to want that exact answer. Sometimes I'm going to want the rounded off answer. The volume of this thing, once again, is 4/3 pi r cubed. I guess I can go right to plug in the radius in. The radius this time is 5, so 5 cubed is a 125, and then times the 4 is a 500. So this is going to give me the volume is 500 over 3 pi meters cubed. And again, if I want to plug this into my calculator, it gives me a 523.60 when I round it off. Okay. So again, really it's just formula based for these guys. I go ahead and plug it in and go from there. Okay. This one here is a little bit trickier because notice that the radius, the diameter, none of that is given here. And there's a couple things that I'm kind of missing from the drawing that we have to assume. We're going to assume that this is a right angle in here, that these are kind of concentric or parallel circles, rather, one above the other. And so what I have is I kind of have a circle drawn at the center of the circle, and that bottom circle, this larger circle down here, would represent, if I knew the pieces of it, would represent things like the radius and diameter of the entire sphere. Okay, and then I have this parallel circle up here. This doesn't represent the radius or diameter of the entire sphere, which is why I can't just use that 4. But what I can do is I can use my Pythagorean theorem to find this missing piece. Okay, and when you look at this missing piece, the thing that you have to keep in mind is like when you think about a circle, if you go from the center of the circle to any point on the circle, that is the radius of the circle. When you think about the sphere, it's kind of the same deal here. If I go from the center to any point on the sphere, then I've identified the radius of the sphere. And so when you look at that line that I've just drawn, that guy right there, that is the radius of this thing. Okay? And so if I can use my Pythagorean theorem, let me take that off to the side. It's 3 squared plus 4 squared equals r squared. That is the radius because it's going from the center of the sphere to any point out on the outside of the sphere. That's the definition of the radius, okay? And so I just used my Pythagorean theorem here. That's going to be a 9 plus 16 equals r squared. I continue to solve this thing. That's 25. The square root of 25 is a 5. And so that's my radius this time, okay? So 5 inches, all right? And now I can come over and plug these away, plug away into my formulas here. So the surface area, once again, is 4 pi r squared, r being a 5 this time. And so for this one, once again, I got the same thing. That's a 100 pi. And again, I can plug it into my calculator. You'll notice that I should get the same values as last time because I ended up having the same radius. Not a great example there, Mr. Jansen. Geez, can't even shake things up for us. Okay, and then once again, the volume, that 4/3 pi r cubed. And again, we plug it in. Inches. And then the rounded off value. Okay, but again, we have to just kind of think about this thing in space, all right? And we're used to thinking about these kind of things when we look at a circle. And with a circle, it's obvious that, you know, any of those is the radius. But with a sphere, it's a little bit harder to kind of depict that or see that sometimes. You know, we could have the radius drawn here and go from the center of the circle to the outside right here, and this would also be 5. And it looks like those are completely different measurements, but again, that's because of perspective, all right? And so when we're kind of visualizing this thing, yeah, based on the perspective, that 5 looks smaller, but it's kind of the angle at which we're looking at it. And it goes back to the nature of 3-dimensional figures being drawn on a 2-dimensional piece of paper. Okay, so we have to really think about which points are being connected and a little bit less about like what does it look like, what does it appear to be, because again, this is drawn kind of funny because it's a 3-dimensional shape being depicted on a 2-dimensional piece of paper. Okay, so we have to kind of take the points that we're connecting pretty literally here. All right. If I look at something like this guy, it says 3 golf balls come packed in a box. How much empty space is left in the box if the diameter of each golf ball is 42.7 millimeters, okay? And this is actually how golf balls a lot of times come packed. They come in little boxes that have the golf balls in them. And basically, the golf balls just fit inside the box. So, you know, the top of this thing is touching this top golf ball up here, okay? Because we don't want those things bouncing around in there. The side of this thing over here is touching those golf balls. So they're kind of squeezed in there pretty tightly, pretty nicely, okay? And so the question is, how much dead space is there in here? How much empty space is there around the golf balls? And so when I kind of think about that, we have to think about the volume of the box, how much actual volume is in there, and then how much is actually being taken up by the golf balls, and then look at the difference between those two to find that dead space. And so for this one, let's talk about the volume of the golf balls this time. And we are talking about volume. Volume. This question has nothing to do with surface area. So the volume of the golf ball is going to be 4/3 pi r cubed. And that's just for one of these golf balls, right? And so keep that in mind. That's just one of the golf balls. And so as I plug this in, it told me that the diameter of the golf ball, of each golf ball, is 42.7. And so the radius then is going to be 21.35. And so as I kind of look at that, let me plug that into the calculator, raise that to the 3rd power. It gives me a little bit of an obnoxious decimal here. And, you know, that's kind of okay in a sense, but I don't necessarily want to use that rounded off answer. So if I'm kind of keeping the exact values here, let's see, that's a 9731.810375, okay? And so if I'm keeping those exact values, that's the volume of one golf ball. And I'm going to jump right to the volume of 3 golf balls here. If we kind of think about that, I'm just going to multiply this by 3. And the reason I want to do that now, it's because it makes my life a little bit easier, because watch what happens here with these fractions. The 3's essentially cancel, okay? So the volume for the golf balls is just that value that I depicted times 4. So let me simplify this a little bit. That's a 38,927.2415. Really kind of cleans this thing up a little bit. That's the volume of all 3 golf balls put together. But now that's not exactly what I want. What I want is the dead space. So now I need to talk about the volume of this box. And because these golf balls, we know that they're kind of tightly packed in here, that the golf balls touch the box on each end, it means that when I look at the distance across this box, it's the same as the distance across the golf ball. In other words, when I look at the dimension of the box over here, it's got to be a 42.7 millimeters. Okay? Because again, it's got to match the radius of that golf ball in order to be able to hold this thing tight. Okay? Likewise, the dimension over here is also 42.7 millimeters. Okay? The top and bottom of this thing have to be a square. And then the height of this thing, the distance the whole way across here from top to bottom, okay? Well, it's the length of essentially 3 golf balls in terms of diameter. So it's going to be the 42.7 times 3, which gives me a 128.1. Okay? And so when I look at the dimensions of this box, if I want to hold those golf balls in there tight, all right, it has to have a length, the base has to have a length and a width of 42.7, and the height has to be the exact height of the 3 golf balls, which is the 128.1. And so now the volume of this thing is the area of the base, which I can find by doing the 42.7 times the 42.7, times the height, because again, this is a rectangular prism this time, and this is how we find the volume of a prism. And this is a job for my calculator, 42.7 times itself, and then times the 128.1. And so what I get for the volume of the box is 23,3563.449. And again, that's cubic millimeters. Well, now that's the volume of the whole box. I want to find the dead space, which is essentially the parts that are not being occupied by the golf balls. And so what I need to do is I need to subtract these two things. So I'm going to take the volume of the box. Sorry, I had my decimal the wrong spot there. The volume of the box minus the volume of the golf ball. And I just realized my golf ball is missing the pi value up here. I forgot to write it. And I haven't plugged that into the calculator yet in terms of pi. I've left it as an exact value because, again, I want to round this thing off at the end. So now this is a job for my calculator. Sorry, I'm still punching it in. Let me make sure I've got it right. There's a lot of numbers going on here. And so when I do the subtraction, I punch in the pi and everything. When I do this, I get an answer of 111,269.91. And I'll just round that off. Cubic millimeters. Okay? That's how much wasted space, that's how much dead space is in this box. Okay? And what's interesting is there are different boxes that sometimes, this is kind of the standard that I've seen golf balls come in. But what if you changed the dimensions of this box? What if you made maybe a triangular box or something like that? Would we be able to cut down on the wasted volume that's in here? That's kind of a question we might be able to answer. If I started changing the different shapes of the box, would I be able to get something that's a little bit more efficient in terms of the dead space?